Welcome back. Let's talk about sets. What I'm going to do is go through these notes that I have posted for the class. You might want to print them out and follow along. I'm just going to read through these and talk about them and scribble things in the margins. All right, let's get started. So sets form the foundation of all mathematics. It's pretty important stuff, like simple things that we think about, like numbers, we sort of take for granted, numbers, counting. Even those things can be defined in simpler terms using sets. So what we're going to use sets for in this class is to develop a vocabulary that we can use to talk about more complicated things. Okay, so we're going to start out simple, and this section on sets is not too hard. You may have seen this in lower levels of school. Sometimes they cover this in grade school, like 6th grade and stuff, at least the basic ideas. So we're going to start off simple, but this is going to provide a vocabulary we're going to use throughout the course. Okay, so a set is a collection of elements or members or things. All right, so just by example, just look at some things that are sets, like integers. The set of integers, that's a set. So mathematically speaking, that's an infinite set. But it's good to point out here that we're dealing with finite computing machines, so we can't represent the entire set of integers. We have to represent a subset of the set of mathematical integers. Another good set is the Led Zeppelin song collection. That's a finite set. All right, there's only so much Led Zeppelin songs, which is a shame, but it's a finite set. Here's another finite set. So here we're using set notation. The set A, we usually use capital letters for the set to indicate a set, and then the elements of the set we put in brackets, or curly brackets rather, with little commas in there. So the elements 1, 2, 3, 4, and 5 are in the set. So there's some special sets we're going to deal with. One is the universal set, and we use the symbol U, capital U, with little lines on top, and our little, font. The font is a special kind of font here. It's hard to draw a U that looks like that doesn't look like another kind of symbol, but you can draw it like that, kind of, with those little straight line parts on top. So a universe has to be defined for a particular problem because we're dealing with finite computers. But even if, in mathematically speaking, it's not practical to talk about the actual universe, with stars and galaxies and stuff. So we have to define the universe for a particular problem. All right, it's just so we can handle it. Another common set is the empty set. So there's a special symbol for that, which is a round circle with a bar through it. This is also sometimes called the null set. All right, so dealing with elements in a set, we have a notation. This little looks kind of like an E thing. Sometimes I'll draw it out like that. And that's element of, and this is not an element of. So 4 is an element of A. We read that thusly, and 8 is not an element of A because there's a 4 inside this set A, but there's no 8. All right, so here's some more finite set examples. Just to round it out, I've got a set A that consists of the elements 3, 6, and 7. There he is. Here's another set that consists of 1, 2, 3, 5, 4. Just some sets, just some finite sets, arbitrary, nothing too deep there. And then here's an empty set. So you can also express the empty set with a set of empty curly brackets. Okay, so here's some infinite sets and notation we use to designate an infinite set. Once again, this is just a mathematical thing because in reality for computing we can't represent an infinite set. We have to deal with a subset of that. But notation speaking, we use this dot 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 to imply an infinite set. So 1, 2, 3, 4, 5, 6, 7, that implies positive integers because we're counting up. And this one here, 1, 3, 5, 7, 9, 11, right? That implies positive odd integers. It could be some other series, but so it's not totally precise. So we once again we use ellipsis, the dot dot dot, to represent an infinite set mathematically. But sometimes that's not adequate. Like for example, this sequence here, 1, 2, 4, 6, 10, 12, 14. What's the pattern? I mean, it's almost even numbers, but there's no 8 and there's no 14. So it's maybe there's a pattern to it, maybe there isn't. It's ambiguous, it's not clear. Okay, this second pattern here, 0, 1, 1, 2, 3, 5, 8, 13, 21, dot, dot, dot. Okay, you might recognize that as the Fibonacci series, but you might not. Okay, so this dot 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 implies an infinite set, but it's not particularly always clear, so we have to have another notation for that. So what we have is such that notation. Okay, so we use this straight bar right here, and we say such that, and it indicates a condition that that designates membership in a set. So this line you would read as the set K equals all the elements X such that X is an even integer. So X is what we use to indicate an element, and then this stuff over here is the condition really that allows for membership. X is an even integer is the condition. So here's some examples. You could say the set L is that all elements Y such that this quadratic is satisfied. So if you solve this quadratic, you get roots 1 and 2. Okay, so it's like another set notation way of indicating that the roots of this quadratic are in the set. This really, we use this mostly because most college students at this level have had this kind of algebra, and we can use it to express certain kinds of problems. Other than that, it's not really particularly useful, mathematically speaking, in my opinion. Anyway, so a little more subtlety to this whole set thing. So one idea is that order and repetitions are irrelevant for a set. Okay, so what we're saying is the set M could be expressed as 7, 3, 6. You could also express it as 7 or 6, 7, 7, 3, 6. So there's 2 7s. It's the same set. It's really just this set. Or you could represent it 3, 6, 7, and that's probably the best way, the most concise way to represent this set, because it's sorted and there's no duplicates. But the point is, these are all the same. That is, the 2 7s don't really count. Okay, so we don't count order and we don't count repetitions. It makes, yeah. If you drew the Venn diagram, what we're talking about is that there's this items 3, 6, and 7 in the set, and we don't. Yeah. All right. So order and repetitions don't matter in a set, but they do in a sequence. Okay, so a sequence is a special kind of set. It's a set where order and duplicates are allowed, or that is, order and duplicates make a difference. Okay, sometimes we call sequences strings, and we have a slightly different notation. We use square brackets. Okay, basically we use square brackets. So here's a sequence A consisting of these elements 1, 2, 3, and 4. So sequence and repetition would matter. So like, for example, the sequence 1, 2, 3, 4 is not equal to the sequence 1, 2, 2, 3, 4. It's a different sequence, right? Or it might make more sense if you think about the elements as letters of the alphabet or characters. So here the sequence B consists of the elements C, A, and T. So sometimes we'll use double quote notation for a sequence. That's why we call it a string. Okay, so this is just like writing cat. You could write it out like this, or you could write it like that. And clearly, cat is not equal to act when you're thinking of strings. Okay, so a sequence is a special kind of string where the order matters and repetition matters. Okay, you can have sets of strings. For example, X is a set, so we're using curly brackets, but the elements of the sets are strings. So you could have a cat, a dog, and a fish. Or you could represent the strings themselves using this sequence notation with square brackets, right? So C, comma A, comma T is the sequence cat, or the string cat, right? And then those three strings are in curly brackets. Okay, that's a lot of commas and stuff, so sometimes we'll leave off the quotes. So really we're leaving off the quotes around cat, dog, and fish just because it's to make it more brief. So here's another example of why is the set of all strings S such that S is in the Scrabble dictionary. So this is a such that notation, not for an infinite set, but for a very large set that you wouldn't be able to recognize. We wouldn't be able to notate concisely some other way. Okay, so it's a very big set of strings. Why is a set of strings S such that the string S is in the Scrabble dictionary? So this is something we do all the time. We build sequences all the time. It's a very human thing to do. So here we do it with digits. Right? So given the set of symbols, digits. So digits is a set of symbols, 0 and 1. Right? So using that, we can build all kinds of sequences that we use to represent numbers, by the way. But you could have another set called values, which is all the possible, let's say you define values as all the possible 2-digit sequences. That's this right here, right? So this values is a set of sequences consisting of all the two-digit sequences that can be made from digits, and it happens to be the numbers 0 through 3 in binary. Okay, so we do that all the time. Like we do that when we count, we do that when we write words, we do that when we speak. We do this all the time. Okay, so for example, take the set alphabet, which is a set of these symbols here. Now we can build all kinds of sequences from that. We could build a set called words, which would consist of these 5 sequences or these 5 strings, and then we can continue that one level up, right? So now words is a set of strings. We can build sequences out of these strings, and we could call that sentences, right? So sentence is another set sentences is a sequence, actually, because sequence is important. It's not important for the set of words. That's just a set of sequences, but we could build a sequence of sequences because sequence is important for sentences, right? That's how we make sense of each other when we speak. That's grammar, right? The order of the words, the sequence, makes grammar. So you could build a sentence: dogs chase cats, which actually makes sense, right? Dogs do chase cats. You know, cats sometimes chase dogs too, but like cat. Chase, that's, makes less sense, but it's still a sequence, but maybe it's not a valid sequence in the language. Okay, we're going to talk more about this when we talk about languages. What are valid sequences for a language? Okay, so this is providing the theory we're going to use all the way to the end of the course, but it starts out by talking about simple things like numbers, like counting, how you can think of numbers as sequences. And we build on that. All right, so let's keep going. So there's something called set equality. So 2 sets can be equal if they have exactly the same elements. So here's a formal definition. So if you were writing a program, you would need to use this formal definition. Okay, so 2 sets are equal. A is equal to B. The set A is equal to the set B if when an element X is in A, then X is also in B, and when that element X is in B, it's also in A. So it has to be in one and the other, and vice versa. So here's 2 sets that are equal. Now remember, order and repetition don't matter for sets. So 2, 3, 4 is a set. B, it's the same set because the double 4s don't matter, and the fact that they're in a different order don't matter. The way you apply this rule is, think if you were writing a program. you would go through every element x of A and check for its presence in B. And then you would do the other side. You could write a loop, right? You'd write a loop and check for every element x in B and then see that it's also in A. So let's do that. Okay, so 2 is in A, it's also in B, good. 3 is in A, it's also in B, good. 4 is in A, it's also in B, good. So that's the first half of this check. Now we got to do the opposite. So let's do the opposite. So 4 is in B, it's also in A, good. 4 is in B, the second 4 is in B, it's also in A, so good. The 2 is in B, it's also in A. The 3 is in B, it's also in A, so it's good. So you have to do both halves of that thing. If you were writing a program, that's what you would do. You would iterate through these guys and then check over here, and then you would iterate through these guys and check over there. Okay, so let's see, what about this one? So this one, they're not the same because let's do it. Let's do the check. Let's do the check on how want this side and then check on that side. So 2, 2 good, 3, 3 good, 4, 4 good. This first one was good. But when we do this side, it's bad. Like 2, 2 good, 3, 3 good, 4, 4 good, 5, no 5, fails. So it fails on the second half of this check. So these are not the same. A is not equal to B. Because there's a 5 in B, but there's no 5 in A, basically. I'm going to skip this quadratic one. You can look at that later if you want, or right now if you want, because you got the pause button. Okay, subsets versus proper subsets. So A is a subset of B is spoken. A is a subset of B. So this is the subset symbol. It's a little, you know, that thing with a bar underneath. Okay, this is, it's half the definition of equality. Okay, it's just if half the definition. We're just looking if elements are in the first set, then they're in the second set, and that's all we care about for subset. So formally, subset definition is half the definition of equality. So we've got some subset examples here. So I got a set A is 2, 3, 4, and then I got a set B 2, 3, 4, 5. Is A a subset of B? So it is, and the way you check is you apply the formal definition. You go through just the elements of A and check if they're also in B, and that's good enough. So 2 is in A, 2 is in B, check. 3, 3, check. 4, 4, check, and we're done. That's enough for A to be considered a subset of B. All right, and here's one that's not a subset of B. Remember, we only have to check if it's in A, then is it also in B. So 1 is in A, 1 is not in B. It fails right there. Okay, so A is not a subset of B because it contains an element that's not also in B. What about this guy right here? 1, 2, 3, is A a subset of A? So we check. 1 is in A, it's also in A. 2 is in A, it's also in A. 3 is in A, it's also in A. Okay, so every element in A is also in A. So therefore A is a subset of A. So basically every set is a subset of itself. All right? So that brings us to the idea of a proper subset. Because sometimes we want to deal with just proper subsets, which, yeah, we'll see that later. So we have this symbol without the line on the bottom. That means proper subset. So formally, a subset, or a set A is a subset of B if, or I misspoke, A is a proper subset of B. A is a proper subset of B if it's a subset and they're not the same. Right? If A is a proper subset of B if A is a subset of B and A is not equal to B. So it looks like this on the Venn diagram. Basically, A needs to be smaller than B to be a proper subset. Okay, so here's an example of something that's a proper subset. So I got 2, 3, and 4 in B, and let's check if it's, first let's check if it's a subset. So 2, 2, 3, 3, 4, 4, so it's a subset. Then we'll check for equality or inequality. We want it to fail on one of these items, so it fails on the 5. There's a 5 here, but no 5 here. So that's enough to fail equality, which is what we want for a proper subset. Just thinking about it kind of like a coder would do, right? You would iterate through these items, checking for presence in here, and that would show subset. And then you would look through these items, checking for that they're not equal, that they're not present in this first guy, and you would terminate the loop at the first exception and return false, right? If you're writing a little function that did that. Okay, here's another example where A is not a proper subset of B. So let's see. Because A is not a proper subset of B because A and B are equal. Okay, so A is a subset of B. It passes the subset test. That is 2, 2, 3, 3, 4, 4. It's in, once again, to be a subset, you have to do this. You say there's a 2 there, so there has to be a 2 there. There is. So check, we're good. There's a 3, 3, check, we're good. 4, 4, there's a check, we're good. So that's enough to prove that it's a subset. But then you check for equality to see if it's a proper subset, to see if A is a proper subset of B. And you check for equality and you find that they are the same by, you check each one across like that, and they're the same. So it's it's not a proper subset because A and B are the same. Okay. There's another example you can look at if you want. Let's move on here. So, all right, so there's some operations or things that we can do to sets, set operations. And sometimes these operations are expressed nicely with these Venn diagrams. Okay, the first one is a complement. So there's several notations for complement. Okay, sometimes they use a little C superscript or a little tick, or sometimes they draw a bar on the top. These are just 3 different notations for the same thing, set complement. So the set complement is all elements of the universe which are not in the set, the original set. So here's a little example expressed with a Venn diagram and with set notation, right? Same problem. So we have a universe that's defined as the elements 1, 2, 3, 4, and 5. So that's the box, is the universe, and it has the elements 1, 2, 3, 4, and 5 somewhere in the box, just anywhere in the box to be in the universe. And then we have a set A, it has the elements 2 and 4. So we draw a circle for set A and we put the 2 and the 4 in there. So everything else that's in the universe must be outside of A, right? Because the universe is the box, it must contain everything. So we put the 1, 3, and the 5 there. So that's what it looks like. So the complement of A is everything that's in the universe but not in the set. It's basically these guys, the 1, the 3, and the 5. All right? So you can think of a complement as subtracting a particular set from the universe. So, in other words, A complement equals the universe minus A. Okay? Okay, then there's set union. Okay, we use a symbol that looks like a real straight U. All right? And the union is defined as all elements of A and all elements of B. Okay, so given 2 sets, we have set A is 1, 3, and 5, and a set B is 2, 3, and 4. The union of A and B is 1, 2, 3, 4, 5. It's the set, the union of AB is the set that contains elements of both of these sets, or contains all elements of both of these sets. So you draw a Venn diagram like this with the A and B overlapping. So note that drawing them overlapping assumes that they have some elements in common. It's possible that they might not have any elements in common, in which case you draw the sets separately. But we'll talk about that in a little bit. But here, you know, they have the element 3 in common. So there's going to be overlap on the Venn diagram. Okay, so yeah, it looks like this. So 1, 3, and 5 are in the A circle, and 2, 3, and 4 are in the B circle, and they both set A and set B both contain the element 3. So that's in this little hatched area in the middle is the 3, because that's the common element. So the common element 3 is also it represents the intersection of these two, which is the next operation that we're going to talk about. So we have the set intersection represented with an upside down straight U. A intersection B is the elements common to A and B. Right? This is pretty basic stuff, isn't it? I mean, most people have seen this way early in school, and so this is kind of a review because we need this vocabulary to build on this stuff. All right, so A is 1, 3, 5, and B is 2, 3, 4. They have a common element 3. So that's the intersection. So the A intersection B is the element 3. It's the set consisting of the element 3. Okay, so it's this hatched area, and here is the intersection. And note that A has no intersection with the set 2, 4. So thinking of 2, 4 as another set, and as a whole nother set, A does not intersect with that set at all. That would be what I drew over here. So if I had a 2 and a 4, which is just a set, we don't have a name for it, but it's a set. And then this is the set A, which has elements 1, 3, and 5. These sets have no intersection. That is to say, the intersection is the empty set. Okay? These sets are disjoint, by the way. That's what we call that. We'll see that in a minute. All right. So another operation you can do is the set difference, so represented by a minus sign. So A minus B, we call that the set difference or the relative complement. Sometimes we'll say A minus B, or sometimes we'll say the set difference A minus B, I guess, or the relative complement. Okay, well, in there we remove the common elements from the first set. So here's an example. Given a set 1, 3, 5 and another set 2, 3, 4, if we subtract 2, 3, 4 from 5, what we're doing is we're subtracting the common elements. So 1, 3, 5 is in this set here, in this circle, and 2, 3, 4 is in this circle over here, and the element they share is 3. So we pull the 3 out of the first set because that's a common element, and we get the answer 1, 5. So it's shown in this hatched area. So formally you could say the set difference A minus B consists of all the elements X that are in A but not in B, right? So you go through A, set A here. 1 is in A, but it's not in B, so that's a member. 3 is in A, but it's also in B, so that's not a member of the answer. 5 is in A, and it's not in B, so that's a member of the answer. You do it like that if you were implementing this in code, right? If you were writing a program to check for these things, right? That's what we're interested in, writing code. Okay, moving right along. Note that order matters. The order of the set matter in the set difference operation. In other words, A minus B is not equal to B minus A. That is, they're not commutative. Like, what is commutativity? It's like addition is commutative, right? You can add things in any order for addition. Multiplication is commutative, but division is not commutative, right? A times B is equal to B times A, but A divided by B is not equal to B divided by A. Okay, so same is true with set difference. It's not commutative. So A minus B is not the same thing as B minus A. Here's an example. So if you took 1, 3, 5 and subtracted 2, 3, 4, you'd pull out the common element 3, and you'd end up with 1, 5. all right? But if you reversed the operations and you did 2, 3, 4 and subtracted 1, 3, 5, you'd pull out the common element 3 out of this first set, and you'd end up with 2, 4 here. And 1, 5 is not equal to 2, 4, okay, so this a minus b is not equal to b minus a. This is a point where we can point out that the set difference can also be given by the intersection with this thing. A minus b can also be expressed as a intersection b complement, right? Because if you did a minus b, what are you doing? You're taking the common element 3 and taking it out of a. What are you doing if you do the complement of b? What is the complement of b? It's 1, 5, 6. So the universe matters here. Okay, the complement of b is 1, 5, and 6, and the union of a with so the union of 1, 5, 3, the union of that with b complement with b complement, which is 1, 5, 6. The union, or the rather the intersection. The intersection of that is 1, 5, which is the same as subtracting out the 3. Okay, so these two are equivalent here. Okay. All right. We've got something called set cardinality. Okay, set cardinality is simply the number of unique elements in the set. Now remember, duplicates don't count. A set with double elements is the same as, a set with a set without those double elements. It's the same set, really. You could sort of think of it that way. Okay, so saying unique is just kind of redundant. But to be clear, we want to point out that duplicates don't matter in a set. So the set cardinality is just how many unique elements are in the set. So for example, this guy. So we'll just deal with sets that have unique elements, just to be clear. But okay, you just count them. So there's 1, 2, 3, 4, there's 4 guys in there. There's 4 things in there. So the cardinality of A, represented with these 2 lines, is 4. It's a little bit like the absolute value symbol. In fact, it is the same symbol, but here it means cardinality, but it's analogous to absolute value. So here's an example so far of summary of everything we've talked about so far, okay? So here's a universe of 0, 1, 2, 3, 4, 5. So everything in this box here, all of these guys are in this box somewhere. They're in the universe somewhere. 0, 1, 2, 3, 4, 5, 6, okay? The universe is in this box somewhere. In A, we just chose A to be 1, 3, 5. So this first circle has A, 1, 2, 5. Then B has 2, 3, 4 in there. Okay? Then if you take A minus B, what you're doing is subtracting the common elements from A. So A has 1, 3, and 5, and B is 3 is a common element, so you take that out and you end up with 1, 5. Okay, B complement is the universe minus B, so it's all these guys that are in the universe but not B, so it's 1, 5, 0, and 6, right? All the guys that are in the universe but not in B. Okay, and what's the intersection of A and B? It's this thing here, right? What's the union? It's all of these guys in the 2 circles. It's 1, 2, 3, 4, 5. What's the cardinality of A? It's the number of items in A, is 3 of them. 1, 3, and 5 is 3 elements. There shouldn't be curlies in here. Cardinality is not a set. Typo. Cardinality is just a number. It's a count. Okay? It's not another symbol. Here, we're just dealing with symbols right here. 1, 2, 3, 4, and 5. Those are just symbols. Okay? But when we talk about cardinality, we're talking about, a number. What we typically think of as a number. All right. A union B complement. So the union of A and B is 1, 2, 3, 4, 5, right? The complement of that is everything in the universe that's not in that union. It'd be 0 and 6. All right? Okay, more fun with sets. Okay, what about precedence rules? Okay, if you have a series of operations that are all the same operation, like here I'm doing 2 unions. So I'm doing A union B union C. Therefore, in this situation, the order of operations does not matter. So I could take A and union it to B, and then take that result and union it to C. That's the same as taking A and union it to C, and then unioning it to B. If they're all the same operation, you get the same result. But here, the same thing for intersection. So I could do 2 intersections. I could do AB intersection first, and then so AB intersection first would be this little pie right here, this little wafer biscuit, kind of looks like a wood biscuit if you do woodworking. This little funny thing here. And then if I intersection that with C, I just get this triangle thingy. I could also do A intersection C would be this little wedgy thingy. And then if I did the intersection of that with B, I'd get this. So the order doesn't matter if you're doing 2 operations of the same type. Now what if you're mixing operations? If you're doing multiple different operations, then you need precedence rules. Okay, so here we have these are the precedence rules. So 0 is really the highest precedence. The highest precedence. So first you do anything that's in parentheses, then you do any complements you might see, then you do intersections, then you do unions. Okay, so for example, if you wrote out A intersection B union C, so here we're doing an intersection and a union. Intersection has a higher precedence, which is the same thing as putting parentheses around the intersection. These parentheses, they just kind of make it clear that we need to do intersection first. All right, so really these 2 expressions are equal, but it's not the same thing. You know, doing the intersection first is not the same thing as doing the union first, as shown over here in Venn diagrams. So this first one I think is I think that's this first expression. See, A intersection B would be this pi right here, right? It would be this thing. This is A intersection. This is A intersection B. And then if I union that with C, I get, you know, I add C all in there. That's what I get. And then the second one, here we're doing the union. We're doing B union C first. So B union C is this, right? That's B union C. And then intersect that with A, and I get this hatched. So, you know, these are not the same. This expression here is not the same as this expression. Okay. All right, moving right along. We've got De Morgan's laws. So, at the high level, the most general case of De Morgan's, the way I like to think about it is you just swap everything. Basically, you swap union with intersection, and then you complement every binary operation. Right? Every operation that has 2 operands, you just complement it. So that means it's helpful to fully parenthesize everything first to identify all the binary operations. Okay? So there's usually they usually simplify De Morgan's down to a couple of examples just to make it simpler to understand. So let's look at those. So one form of De Morgan's is this. So here we have an intersection, and then we have two operands here. So put a parens around those, and this one happens to be complemented. Okay, then you just swap everything. So you swap this with a union, and this complement you swap with a not complement, and you do that to the A and B as well. Okay, so the intersection here becomes a union here. The complement on the parens becomes a not complement. The no complement on A becomes a complement on A, and the no complement on B becomes a complement on B, right? So you just swap everything. Okay. This is just showing how these two expressions are equal, and you know, you can imagine this to be either one of these because they're the same. Like, let's see, which one do you want to do? So the intersection of A and B would be this little thing in the middle. Well, the complement of that would be everything outside that. That's thinking about it this way. Now, if you thought about it this way, everything outside of A would be all of this stuff out here, and everything outside of B would be all of this stuff out there, and the union of that would be all of this hatched stuff. So just different ways to think about that these are the same, and there's just one diagram here because they are the same. So here's another form of De Morgan's that you might run across. A complement union B complement. So you need to put the parens on there first to identify that. Well, there needs to be a parens on every binary operation. Union is a binary operation. That is, there's two operands. Okay, complement is a unary operation. The complement only applies to A here. So the operand for this complement is A. The operand for this complement is B. But the union has two operands. There's this side and this side. So the union is a binary operation. The complement is a unary operation. So you take the every binary operation and you put a parenthesis on it. So that's what I've done. I've added the parentheses on this, and then for that parenthesis you can see that there's no complement. So then we apply De Morgan's and we just switch everything. So the no complement here, we put a complement, and the complement here we remove there, and the complement here we remove there, and then the union we switch to intersection. All right. So this De Morgan's, or this Venn diagram is trying to show that these all of these three expressions are the same thing. So generally speaking, we just switch everything. So here's one more De Morgan's where I've got a complement on the A, but no complement on the B, and then I've got a complement on the parens for this binary intersection operation. So you just switch everything. You get rid of the complement on the parens. You switch the intersection to union. You get rid of the complement on the A, and you add a complement on the B. Just flip everything. Okay, moving right along. Definitions. Something called disjoint sets. So definition, a set is said, or rather this applies to two sets. So two sets are said to be disjoint if they do not share any common elements. So that means if you try to take their intersection, you would just get the empty set. All right. Here's some examples. So here's a couple of sets that are disjoint, represented with set notation here and then Venn diagrams here. So A is 1, 3, 5 and B is 2, 4, 6. So they share no common elements. So their intersection is the empty set. And represented this way, you can see there's no common elements. There's 1, 3, 5 and 2, 4, 6. So these are disjoint sets. A and B are disjoint sets. All right. that lets us talk about set partitions. Okay, so a set partition is a collection, or rather another set of sets, and those sets are disjoint. That means they share no common elements, but their union is the original set A. Okay, so a simple way to think about it is you're taking a set and just chopping it up. You're cutting it into pieces. So they're not going to share any common elements when you do that, right? When you just cut it with a knife, you know, a straight line, right? So, okay. So I have a set, original set A, and I've cut it here, and I've cut it here, and I've formed three sets. I formed set B, item 2 and 3. I formed set C, which has item 4. And I formed set D, which has item 1, 5, and 6. All of these sets are disjoint from each other. B and C share no common elements, and none of these share any common elements. But together, when you union them all together, you form the original set A. Okay, so a partition is it's the set of sets B, C, and D, and B, C, and D are disjoint. And when you union B, C, and D, you get the original set A. Okay, so that's what this is saying in set notation. Yeah. Right? 1, 2, 3, 4, 5, 6. You could make B is 2, 3. There it is. C is 4. There it is. D is 1, 5, 6. There it is. Their intersections are the empty set. That is, they share no common elements. B, C, and D are disjoint. But when you union B, C, and D together, you get A. That's what a partition is. We're just taking A and chopping it up. Let's see. Yeah. Okay, you can have sets of sets, which we just sort of did. When we talk about partitions, a partition itself is a set of sets. But let's talk about set of sets a little more formally, so that we can deal with that a little more clear-headed. All right. So so here's a set of sets idea, talking about it. So given a universe 1, 2, 3, 4, then this universe has a cardinality. There's 4 elements in it. So 4 is not an element here, just to be clear. 4 is just the number 4. When here, 1, 2, 3, 4, we're just dealing with symbols. We like to use numbers, but they're just symbols. Could be, you know, dog, cat, fish, you know, elephant, something like that. They're just things. Thing 1, thing 2, thing 3, thing 4, you know. All right. But the universe, or the cardinality of this particular universe, is 4 because there are 4 elements in it. It has nothing to do with this 4. Okay, you can make all kinds of sets out of this universe. All kinds. There's so many combinations. But here's one. Like, you could make a subset 1, 3. Subset of this universe. You could make a set 1, 3. You could make another set 2, 3. You could make another set 1, 2, 4. You could make the empty set. So this is just one possible set, right? It has the curly brackets on the outside. S is a set, and its elements are sets. So S is a set of sets. So what is the cardinality of S? S is a set. What's the cardinality? You got this guy, you got this guy, you got this guy, you got this guy, kinda. So there's 4 if you count this guy. If you count the empty set as an element, then the cardinality of S is 4. So you may have a problem, you may have an issue with counting nothing as something, and I totally get that. But so this is kind of a philosophical issue: is can you count nothing as something? So if you're in, you know, your philosophy class or your mathematics class, let them spend hours and hours on that. But for us, we need to write a program. So we're going to count the empty set as something if it makes our code easier. And if it doesn't, we're not going to count it as anything. Okay, so incidentally, I think this is the main difference between Democrats and Republicans, is one of them counts nothing as something and the other one counts something as nothing. There's something. Did I say that right? That's just a joke, silly joke. Okay, so moving right along, we've got something called the power set. And yeah, so the power set is the set of all possible subsets. So in this previous example, I just gave you one possible set of subsets. But what is the set of all possible subsets? And so here, in this example, we're saying we're going to start with a set A. We're going to generate the power set of A, and then we're going to look at the cardinality of the power set of A. So here's a set A, consisting of the elements little a, little b, little c. Okay, just before we go any further, how many elements are in A? 3. So the cardinality of A is 3. Okay. Then what are all the possible subsets that you can make from A? Right? There's all kinds of subsets that you could make out of here. A, right? You could take out little a and that'd be a subset. Or you could take out little b and that'd be a subset. You could take out little c, that'd be a subset. Or you could take out AB, that'd be a subset. Or BC. So what are all the possible subsets that you could make out of capital set capital A? Okay, well, you can be systematically about that. You could say, well, what are all the sets of size 0? That would just be the empty set. And there's one of those, right? How many subsets can you pull out of here of size 1? Well, little a is a subset, little b is a subset, little c is a subset. There's 3 of those. How many subsets have 2 elements? How many subsets have a how many subsets have a cardinality of size 2? Well, the subset AB has 2 elements, the subset AC has 2 elements, the subset BC has 2 elements. Okay, so there's 3 of those. What about the subset CB? What about that? Well, that's the same as BC. So that's not a separate element because these are the same set. So these are the same. So there's just these 3. And what about all the subsets of this guy here that have 3 elements? It's just this. Because remember, we're not talking about a proper subset, we're talking about a subset. So for a subset can be equal to the original set and still be a subset. Don't confuse subset with proper subset. Okay, well anyway, there's one of those. So altogether there's 3, 4, 5, 6, 7, 8 of those guys. It's no coincidence there's 8. There's 3 in the original set, and there's 8 here. So the power set of A is the set of all possible subsets. It's all of these guys. So that's a subset of A, this is a subset of A. All of these guys here, that right there, all of these guys are subsets of A. So this is all the possible subsets you could make. There's 8 of them. And it's related to if you represented them using bits. So if you did A, B, and C and used bits, then the empty set would be 0, 0, 0, and the set A would be 1, 0, 0. Okay, and the set B would be 0, 1, 0. If you just have a bit present in what we're calling a bit vector, a 3-bit bit vector, the presence of a bit indicates membership in the set. Okay, so the empty set is 0, 0, 0. This is A. This one here is B. This one here is C. This one here is AB, right? 1, 1, 0 would be AB in this representation. And so forth. Well, how many combinations of 3 bits are there? There's 8 of these, right? There's 8 combinations. So so that's where you get this thing here. This the cardinality of the power set is 2 raised to the power of the cardinality of the original set. You shouldn't have a -1 on there. If you count the empty set, then the cardinality is 2 to the cardinality of A. If you don't count it, then it's 2 to the cardinality of A minus 1. All right. So that's the power set. How are we doing on this stuff? It's coming up on an hour on this junk. Okay, a couple of examples here, and then we'll stop. So here's an example of using set theory to solve a problem. All right. So say you're given this informations here. You're told that there's a universe of 10 students. So here are the numbers inside these sets are quantities. They're not really symbols. Okay, these are quantities now. Okay, before we've been using numbers as just symbols, because we're running out of symbols. We got capital letters, lowercase letters. We can only do so much. So here these are actually numbers. So you're told that 3 students are taking programming, P, and math. There's 3 that are taking both of those courses. So that's this 3 in here. There should be 3 students in here. I could, just to be clear, there's 10 students, it could be Bob, Sue, Ted, and Sam. So basically Bob, Sue, and Ted can be in here. There's 3 people in here. I don't know who they are though, so it's just 3. Okay, so we're just going to use 3 because there's 3 students. I don't know who they are. Okay, and then you're told, that 4 are taking math. So, well, I already got 3 in the math union circle, so there must be 1 more in here. So you put a 1 in there, and then there's 6 students are taking programming. So I've already got 3 in the programming circle, so there must be another 3. So there's 3, 4, 5, 6, 7 students, and there must be 3 that are not taking either one of these classes. So that's the question. How many students are taking nothing? 3. Yeah. Or maybe you could say, how many students are not taking either programming or math? 3, because they could be in another class maybe. Anyway, okay, here's a good one. So there's this guy, Elon Musk. I don't know, some of you may have heard of him, and he has this idea of going to Mars, which I'm still trying to wrap my head around. So here's a little problem. So let's say the set A is all people who want to go to Mars. Okay, and B is all the people who can actually afford to go to Mars, because you're going to have to pay, right? It's going to be, big chunk of money for a rocket ride to Mars. Okay, so here's the way it works out. So me and Elon, I'd like to go to Mars, and Elon Musk would like to go to Mars, so we're in set A. But the people who can actually afford to go to Mars, like Elon Musk has the money to go to Mars, and my wife has the money to go to Mars. So the intersection of people who want to go to Mars and actually can go to Mars is just Elon. He's just going to go there by himself because I can't afford it. All right? If you want some fun in today's political climate, Google intersectionality Venn diagrams. It's fun, depending if you're going to get offended or something. I don't know. But anyway, okay, a couple of more problems here. So here's a just problems, right? We're just working problems now for a while. So here's a universe 1, 2, 3 all the way to 10. So we're implying the integers with the ellipsis dot dot dot. We're implying just the integers 4, 5, 6, 7, 8, 9. Okay. So A is 1, 4, 7, and 10, just arbitrary, and B is these guys, and C is these guys. So what is this? What is this expression? B complement intersection of quantity C minus A. So you got to do this in pieces, right? So first thing you do is take the complement of B. So the complement of B is everything in the universe that's not in B, right? So 1, 2, 3, 4, 5. So 6, 7, 8, 9, 10, right? 6, 7, 8, 9, 10 would be B complement because it's everything in the universe, everything in U. U is 1 through 10, and B is 1 through 5. So, you know, B complement is 6 through 10. And then C minus A is everything in C that's not also in A. So you pull the common elements out of C. So you just go through this. 2 is not in A, so you leave it. 4 is in A, so you take it out. 6 is not in A, 8 is not in A, so you take out the 4. All right, so C complement is 2, 6, 8. Okay, then you intersect these two guys, right? We found C minus A and we found B complement. So the intersection of these two guys is what? The 6 and the 8, right? There's there's a 2 but no 2. There's a 6 and a 6. That's good. There's an 8 and an 8. That's good. So the 6 and the 8 are common. So that's the answer. Okay, you could probably write it out with a, you know, I mean, I don't know if I want to do that though, because you could write it out with a universe, but it's gonna be it's gonna take me a while. I don't know if I want to. Should I try? What do you think? So there's the universe. Okay, A is one. What are the? You got to be careful of the complement. So these guys may. Let's assume that they are going to overlap like that. I'm not really sure about that, but okay, 1 is in B and A, but not in C. Right? 2 is in B and C, but not in A. Okay, 3 is just in B. 4 is in all 4 of these guys. 5 is just in B. 6 is just in C. 7 is just in A. 8 is just in C. 9 is in none of these guys. And 10 is just in A. I think that's right. So let's see. We could maybe check it with some of these things. So B complement is, yeah, everything outside of B is 6, 7, oh no. This 8. 8 is just in C. There we go. So B complement is 6, 7, 8, 9, 10. Yeah, good, right? It's everything outside of B. Okay, C minus A is 2, 6, 8. Yep. And B complement, we did that already. And I think it's good, right? I'm just gonna stop there. Send me an email or something if you think I messed up. All right, let's do this one. What's the Venn diagram for A union B minus B? So A union B is these two thingies. And then if we subtract B, you get that. Kind of looks like a Pac-Man. What are all the possible partitions of little a, b? So we're talking about partitions, not subsets. Okay, remember the power set was the set of all possible subsets. That's not what we're talking about here. We're talking about partitions. Okay, so how many ways are there to chop up this So we're cutting it up so we can eat it. Think of this as a cookie. So I could eat the whole cookie. That would be my preference. So that would be little ab. Or we could share the cookie. So there's this, or we could share the cookie and you could get little a and I could get little b. And that's about the only way we could cut it up, unless nobody gets any cookies. All right, so this is all the possible. Okay? I guess there's no way to cut up something so that nobody gets anything. That's not possible, right? I've never had that happen at dinner. Maybe you have. All right. What are all the possible partitions of ABC? So there's another, we're going somewhere with this. What are all the possible partitions of the set, little a, little b, little c? So what we're talking about, we got this, we got a cookie. And so once again, I could eat a whole cookie. Or I could eat this much cookie and you could eat that much cookie. That would be this thing. Or we're just trying to chop this up. We're just trying to. So you could cut it up like that, and somebody could get A and C, and somebody could get B. Or you could cut it up like that. Or you could share it with 3 people. Like you could do it like that. That's all the possible ways to cut up ABC. That's all the possible partitions. So there's 1, 2, 3, 4, 5 of those guys. Okay, so we went from when we had a set of 2 elements, there was 2 possible partitions, and we have a set of 3 elements. There's 5. It's getting bigger. It's getting big pretty quick. What about if we add one more thing in the, one more person to share with? Now, right? Now you invite, 4. So you got 2 kids now. You got mommy, daddy, and 2 kids. And now what are you going to have? Now how do you share stuff? Now it's getting really complicated. So I could just eat everything. That would be A, B, C, D. Once again, that's always my preference. Just let me eat everything. Or you could, I could eat everything and then, or I could eat this much and then you could divide it up this way. I'm not sure the eating thing is the perfect analogy, but you could divide it up this way. Or you could just take B out. And there's all these there's 4 ways to do this, right? Just take 1 out. There's 4 ways. Okay, then there's, you could take A out and then divide up all the remaining B, C, and D. And we've already established that there's 5 ways to do that. Thinking recursively here, right? In other words, if I just take out A and then B, C, and D, I do this B, C, and D the way that I did it up here. There's 5 ways to cut this up. And then I could take B out and cut up the other 5, and C out and cut up the other 3 in 5 ways. Or I could take D out and cut up the other 3 in 5 ways, like that. And many, many, many more, right? I could take out AB, and then I'd have AB split up, which we did the first time, and CD split up, which we did the first time. And you could generate certain patterns like that. The point is, with just 4 of these, there's lots. We're already at 5, 10, 15, 20 something with just adding 1 more element. Okay, this goes incredibly fast. And I've kind of been working on a recursive solution to this problem. I'm just kind of interested how that would work out, but I haven't got anything solved yet. Let me know if you ever figure that out. All right, 2 more problems, and then that's it. Okay, so Mr. De Morgan, let's just look at a De Morgan thing. So Mr. De Morgan said this. He said that if you have these series of operations, this is just a random example series of operations, but let's apply De Morgan's to this. So remember, we need to fully parenthesize this thing, because this B intersection C results in something, box, let's call it union A box. So this becomes a binary operation we need to put in brackets so that we can do the not, right? Not the not, anti-not, or whatever. Okay, so that's where the square brackets come in. I'm just applying square brackets for this union operation right here, right? And then you just flip everything. So A tick becomes just A, union becomes intersection, B tick becomes, okay, I haven't done anything to the inside operation because we're just doing it binary at a time. Okay, so we're not doing anything to what's inside these inner parentheses. I could do that out here, but let's just finish this. So this union becomes intersection, then this tick becomes no tick, and this no tick becomes tick. I could, if I wanted, I could apply. So now do the BC thing. Do the BC thing. The BC. So carry over this stuff. Just carry over the A and this and the bracket and that, and then do this stuff inside. Okay, so now that becomes B intersection C, and you throw a tick on here. All right. These are all just to show that these are all the same. You know. Let's see. I think I'm trying to verify that. I'm just trying to build this A tick union B intersection C. That's the first one. That's this box down here is this. I'm trying to build that. I'm trying to build this expression just piece by piece. 1, 2, 3, 4. That you end up with this. So you do A naught first. This is A naught. Everything outside of A. Then this is this part of it. This is the intersection of B and C. This is the intersection of B and C. Union complement, which is the same as intersection not complement. You know, it's the same thing in there, which is the same as this, and that's what's happening here. This is intersection, and then union that with, or take A and let's see, A naught is this stuff, B intersection C is this stuff, the union of these two is this thing. Or you could do the right hand side of the expression, which would be the union of B naught and C naught. It's everything outside of B and everything outside of C is this thing. And then you can intersection that with A. It would be just this, right? If you took this and intersection that with A. And then if you took the complement of that, you get this, which is this complement right here. So you spend some time on that if you want, and look at those things. One more example. So I often hear as an instructor, students come up to me and they tell me, I know C++, but I don't know C. They tell me that. I hear that. I'm puzzled by that all the time. But in my mind, that's not an okay thing to say to your teacher. And because here's the deal, like there's this C programming language that's been around for a long time, and then they came out with C++, and what they did is they added a bunch more features onto C. So for the most part, C++ is superset of C, or flip that around. C is a subset of C. So if you say you know C++, then you must know C. So this doesn't make any sense. People claiming to know C++ but not know C. This is what they're saying when they say that, which is an odd thing to say. Like how can you know C++ and say you don't know what a variable is, or you don't know what a function call is, or you don't know what a for loop is, or you don't know what an array is. You know, there's all these things you say you don't know, but you know C++. It doesn't make any sense. So, but that's what that looks like. Okay, there's a Monty Python skit where the guy can't say the letter C. It's pretty funny. All right, I think we're done, because the rest of this stuff is the software stuff, and I think I'll make that in another video. Right now, you guys need to do the homework, the bookwork, that is. Do the bookwork, do all the set problems, let that gel for a little bit, and then we can talk about the software implementations of this stuff. Okay, I hope this was helpful to you. I'll see you next time. Thanks for your attention. Bye-bye.